All right, welcome everyone. We'll get started right away here. Some announcements before we get started. You'll have another Achieve as usual. I'm sure you're all used to the pattern. Today, the Chemistry Club has glasses that you can wear to watch the solar eclipse, which will be at about 2 p.m. But they'll start giving away the glasses, I heard, at noon, so right after class, if you want to grab some of them. And if you're able to go outside at 2-ish, I think they'll be outside around 1:45. We'll be there to watch the eclipse. There'll also be some high school students there. So there's like 30 students from Loyola High School here today they're kind of moving around all over, but they'll be with us with the solar eclipse. And I hear there's going to be liquid nitrogen ice cream as well. So that might just be for the high school students, but maybe not. I'm not totally sure. But if you're able to, I encourage you all to be there. Also, this Thursday, Chemistry Club is hosting a speaker in the evening. So it's in this room, but at 5:30 p.m. The speaker is, it's right here. She's the chair of the Department of Biological Chemistry at U of M. She's going to talk about both her research in, it says about how cells sense and respond to membrane damage. She's going to talk about that. And she's going to talk about careers in biochemistry. So I also encourage you all to attend that as well. It's nice to meet another professor and someone from another school, someone that has a lot of valuable things to share. So that's Thursday. You do need to pre-register. There are flyers with the QR code around the building. There's one outside my office as well. And then I will post the flyer as a Blackboard announcement. All right, end of class Friday. We're talking all about these titration curves with a weak acid titrating with a strong base, and then how to calculate the pH at different positions along the curve. And so we started this practice problem where there are 3 different points that we're calculating the pH for. First is before any base is added. So just that weak acid solution, what's the pH of that? Then at the equivalence point, which we're about to do, and then after the equivalence point has been reached and more base is added. So the pH continues to increase. We're getting more and more basic as base is being added to the weak acid. Now remember that we had all of these different equations for different points of the reaction or of the titration to calculate pH. So we did that one already. And we're about to get to the question where we're calculating pH at the equivalence point. For a weak acid being titrated with a strong base, we need to get to this equation here and then eventually calculate pH. So that means we need Kb and we will need conjugate base concentration. So on this next part of the question, we're going to be looking for Kb and conjugate base concentration. Okay, so just remember the question says that we have 40 mils of a 0.5 molar formic acid solution, so a weak acid. It's titrated with a 0.5 molar solution of sodium hydroxide, and then we are determining the pH at the equivalence point. So what's important here, before we even do any calculations, is to think about what is present in solution. And the ratio of the acid and the base is also important. So for every 1 mole of formic acid, it has 1 acidic proton. It will react with 1 mole of sodium hydroxide. So we'll say the stoichiometric of acid to base is 1:1, and concentrations of the acidic solution and the basic solution are equal. They're both 0.5 molar. So if you have 40 mils of a 0.5 molar formic acid solution, that contains some number of moles of the acid. Now, if you have a weak acid solution, you're adding base to it. The base that we're adding here is a strong base. That's going to react with any acid that's present. So if the equivalence point has been reached, that means that all of the acid molecules that were present in the solution before the base was added has been neutralized or reacted with the base. And that can only occur if we have the same number of acid moles, same moles of the acid and same moles of the base. So the equivalence point will be when there's the same number of moles of the base as there is the acid. They're the same concentration. So to have the same number of moles, we need the same volume of that basic solution. So the equivalence point will be when 40.0 milliliters, which is 0.040 liters of NaOH is added. At this point, the moles of the acid in solution equals the moles of the base in solution. Again, because we have same concentrations for both solutions. So this also means that at the equivalence point, the total volume is the 40 milliliters from the original solution plus the 40 milliliters of the base titrant solution. So total volume is 80 milliliters or 0.08 liters. We're going to end up needing that as well. Okay, so when a weak acid reacts with a strong base, all of the weak acid present will convert into its conjugate base. So however many moles of the acid are present initially, that will be the number of moles of the conjugate base that's present. And remember, we're trying to find concentration of the acid's conjugate base to calculate the pH eventually. So we need to find concentration of CHO2 minus conjugate base of formic acid. All right, so where we can start is finding or calculating the moles of formic acid present in solution. Then we know that number of moles of formic acid present, all of it converts to conjugate base. So that will be moles of conjugate base, and then we divide by total volume. So moles of acid added not added, let's say in original solution. $40 milliliters is 0.040 liters, and then we just multiply by concentration, 0.500 moles per liter. I'll draw a line here to separate. Okay, so in that solution that is being analyzed by adding the titrant, there are 0.02 moles of formic acid. As the strong base is added and when the equivalence point is reached, all of that converts to the conjugate base. So now there are also 0.0200 moles of the conjugate base after the equivalence point is reached. So to find concentration of that, I'm going to add a note here, all converts Okay, so all of the 0.02 moles of the acid converted to the conjugate base at the equivalence point. So we know the moles of conjugate base present. Now we divide by total volume. At the equivalence point, the total volume is the 0.08 liters. Okay, so we've got conjugate base concentration, but remember in that calculation we need to do square root of Kb times conjugate base concentration. So we need Kb, but in the question statement we're given Ka, but we can do a simple conversion where Kb is Kw divided by Ka. I'm just going to plug in values and calculate now. Okay, so Kw, constant value, Ka provided in the question statement. We've got Kb, 5.6 times 10 to the negative 11. Now, POH, we're almost there. Negative log of Kb, 5.6 times 10 to the negative 11, times concentration, 0.250 molar. Yes. So we use Kb here because there's no acid in solution. It's all base now. All of the acid was neutralized by the base. So for a weak acid titrated with a strong base, we need Kb at the equivalence point. If it's the opposite, if you have a weak base being titrated with a strong acid, then you need Ka at the equivalence point. Okay, so we've got POH, now pH 14. minus pH, POH. 8.57 as the final pH. So the key piece of information that you need to do all of these calculations is to know that the acid and base react in a 1-to-1 ratio, 1 OH minus for every base and 1 H plus for every acid, and that the equivalence point is reached when the amount of moles of acid are equal to the amount of moles of base that were added. And that's how we got total volume to be 80. Now we can proceed with calculating concentration and then eventually pH. Okay, questions on this one? Okay, let's keep going to this last part of the question. So now, same scenario, we've added the 40 mils to reach the equivalence point. The equivalence point has been reached, and then another 2 mils of the excess base has been added. So the pH should increase even further because more base is being added. We're calculating what that pH actually is. Okay, so now all of the acid reacted with the base, that was all neutralized. The pH of the solution will be dependent on the amount of excess NaOH that's added. So we need to find the moles of NaOH that were added in excess that did not react with the acid, because all of the acid already reacted at the equivalence point, and then divide that by the total volume. So this one will be a little bit less involved than the last slide. So we need amount, or we'll say moles of excess NaOH added. And really what we care about is the OH minus ions. And so that is the liters, which is 2 milliliters is 0.002 liters. And then concentration is still 0.5 moles per liter. Okay, so we've got number of moles added in the 2 mils, but it's added to a solution that already had 80 milliliters of liquid present. And we knew that from the equivalence point. So the total volume is 80 plus this 2 extra milliliters. (82 milliliters or 0.082 liters). So the OH minus concentration in that full solution is 0.001 moles divided by 0.082 liters. Okay, so we're looking for pH. We've got OH minus concentration. We can calculate POH. Negative log of OH minus concentration. Okay. So with OH minus concentration, you directly calculate pOH and then convert to pH. pH 12.09, this is a higher pH than the previous slide. We expect that because we've added more base. So the pH should increase, and that's a way to double check your calculations. Okay. As you're finishing up, any questions on this question? Yeah.
I just usually they would do the KH and you were doing like that
Mm-hmm.
or you're gonna use the KH. Usually
so it depends if you have a weak acid that's being titrated with a strong base, then you use Kv. If you have a weak base being titrated with a strong acid, so the two are switched, then you use Ka at the equivalence point. Yeah. So for what we've done in our notes so far is all weak acid titrated with a strong base. This next slide, I just have one slide to kind of summarize it instead of going through each step. The weak base being titrated with a strong acid, you almost go in reverse for all these calculations. So for A is like the end of the previous titration where all you have present is base. No acid has been added yet, so you can calculate pH by first calculating pOH. There's only base is present. And then we would kind of go opposite. So at the equivalence point, you'll use Ka because we already have a strong acid. And then down here at the end is acidic. So I know you had a achieve that kind of worked backwards. And then also in the book, there's a video that describes or does an example problem going through all of those steps as well in this chapter. So very similar to the weak acid titration curve, but the pH is initially much higher because we're starting with a base. And then as acid is added, the pH decreases according with the acid. And then equivalence point is less than 7. We have a weak base and a strong acid. So the strong acid influences that equivalence point to be low pH. And then one more thing to review here is that some acids, and I think you worked through this in lab, some acids have more than one proton that are acidic. So more than one proton they can give away. Usually, well, always one proton is more acidic than the other. I guess not always. There are some exceptions, but usually one is more acidic than the other. So for a polyprotic acid, it will have 2 equivalence points. And you can identify those by where the line is more vertical. So this first equivalence point is when all of the first proton, the most acidic proton, has been reacted with the base. And then the second equivalence point will be when the second acidic proton, all of that has reacted with the base. So if you see the 2 equivalence points or 3, that means you have a polyprotic acid. All right, I think we're done with that section. Questions before we move on? Okay, so it is useful when doing a titration to know when the equivalence point is reached because that's when you know however much base, assuming you have a weak acid in your container and a base in the burette, that's how you know all of that base has reacted with the acid. So the equivalence point, now if you don't have an indicator, which I think you've worked with, where it changes color, if you don't have an indicator, how do you ever know that the equivalence point is reached? Everything would just stay clear and you'd never know if you reach that equivalence point. It wouldn't look any different in your solution. So the indicator is something that's added that will change color at the equivalence point, or that's the point of it, to change color at the equivalence point to indicate to the researcher, the person doing the experiment, that the equivalence point has been reached. So indicators in general will have 2 forms in equilibrium, and each one will have a different color, or one version of it is clear and the other one has a color. So each form, we'll say, is a different color. And this is usually a weak acid or base that's not interfering with your titration experiment, but it will change color near its pKa. So you can use pKa values to help identify a good indicator for a certain titration. So an appropriate indicator for a particular titration must change color over a range that overlaps or is close to the equivalence point. Or we'll say the pH at the equivalence point. So for example, we're going to stick with that weak acid example. We have a weak acid being titrated with a strong base. The equivalence point will be somewhere between, it'll be above 7, so somewhere between usually 8 and 10 will be the pH at the equivalence point. And so this indicator, phenolphthalein, is a common indicator for weak acids being titrated with a strong base because it changes color between 8.2 and 10 pH, the pH value, when the pH is between 8.2 and 10. And usually for weak acids, the pH of the equivalence point is between 8 and 10. So it will change color once that pH is reached, and then you'd know by the experiment that you've reached the equivalence point. It can also be used for strong acid-base titrations where the equivalence point is 7. It would just tell you when you've just passed the equivalence point as it starts to change color. Okay, with this in mind, here's the first iClicker. Let me start it here. So you're selecting 2 appropriate indicators. You'll only be able to select one in iClicker, but look at this table to find the other one that would also be appropriate for the titration of this acid with a strong base, where the equivalence point is 9.3. So on this table here, there will be 2, but you can the only one of them is an option for you on iClicker, but try to identify both. Yep. Yeah, you want the pH range for the color change to overlap with the pH of the equivalent point. You tell me? Okay. All right, let's say like 10 more seconds. It looks like everyone has submitted. All good? Anyone submitting? Okay, I will end it here. Let's see what we're looking. Okay, pretty good. So this pH 9.3, we want the pH range of the color change to overlap with pH of 9.3. So of your options, the phenolphthalein, that was kind of obvious from the previous slide, which I didn't realize when I put this iClicker together, but that's okay. That is a good option. The other good option would be just past the titration pH because we're adding base, so the pH will continue to rise. So that would be this last one here, the yellow. Everything else is below the titration equivalence point, but it will be phenolphthalein and alizarin, yellow, R. Okay, so actually that's it for this section. We're going to move to talking about solids in solution. So we're done with titrations, done with acid-base chemistry. The last couple of sections are more simple, I think. But this whole chapter is called aqueous equilibria. And you might remember back to Gen Chem 1, here's a little bit of review for you. Remember we had solubility rules where like first column metals will always become ions, seventh column halogens will always become ions in solutions. And then we grouped certain combinations as soluble or not soluble. But it's actually a range. Some solids are very minimally soluble, and we say that those solids are in equilibrium when they're in solution. They're in equilibrium with their ions. So that's kind of what we're focusing on for this section. And we'll talk about what KSP is. But first, heterogeneous equilibria. This is when species in different phases so solids, liquids, gases are the different phases when they interact with each other or when they're in equilibrium with each other. So here we're looking at solid phase in equilibrium with aqueous phase. This is an example of, actually let's talk about sodium chloride first. So sodium chloride, that's a first column metal, seventh column nonmetal. Those will always ionize, but they can only ionize to a point. Imagine you had like 1 milliliter of water and you kept adding sodium chloride to it. There's only so much sodium chloride that can dissolve in that. So once you have passed the saturation point where all of the ions that can dissolve in that volume have dissolved, and you add more solid, that solid will remain a solid. But now we say that solid is in equilibrium with its aqueous phase. This is another example that we saw last term. I think we were talking about ionic equations. But this solid, so lead iodide, when you add to solution, most of it becomes a solid, but some of it remains in the aqueous solution. So by convention, we have, for these equilibrium reactions or equilibria here, the solid on the right side and the ions on the left side. You'll see it represented both ways, but if you had to choose, by convention, we put the solid on the right. But these two sides are in equilibrium with each other, so it doesn't matter too much, but it will be helpful with what we're doing on the next slide. So here we'll talk about this KSP, which is, the SP stands for solubility product. It's the same K that we've talked about in the past, except when we're looking at solids becoming ions, it doesn't matter which side of the equation the ions are on, they will always be in the numerator for KSP. So KSP is the product of the concentration of the substance's ions in solution, each raised to the power of the ions coefficient in the valence chemical equation. So for the equation that we just looked at, we have solid on the right side, aqueous on the left side. The KSP is, we're keeping the ions in the numerator. Even though they're on the reactant side, for a solid, for KSP, ions will always be in the numerator. So we'll have concentration of lead 2+ times concentration of iodide minus, and then squared because of its coefficient there. And that's it. We don't put solids in equilibrium expression, only aqueous or gaseous substances, and the ions are always in the numerator. So if we look at this other example, barium phosphate, which forms barium ions and phosphate ions, we can write KSP just by using those ions in the balanced chemical equation and their coefficients. So we have barium 2 plus, concentration cubed, and then phosphate concentration squared. So just to write that down, always include ions in numerator. Never include solids. So this is for KSP specifically. When you're ready, go to the next slide. So this will be another iClicker for you. We have iron 2 sulfide. Here's some more review. I'm going to go to this slide now. I can go back to this if you need to in a moment. Iron 2 sulfide, that 2, remember transition metals? Most of them can have multiple cationic charges. So the 2 Roman numeral in parentheses in the name indicates the charge of that transition metal. So we know from the name that iron has a +2 charge because of that 2 in Roman numerals. And then iron 2 sulfide, well, you should try writing out that ionic compound formula as a solid. More review. So iron 2 sulfide contains a saturated solution, contains 4 times 10 to the negative 10 molar of iron ions and 4 times 10 to the negative 10 molar sulfide ions, and you're calculating KSP. So I will get this started. Yep. Yeah, so that's because there was 40 mils of the weak acid present originally.
So we just add 40.
Because for the equivalence point to be reached, the same amount of the base had to have been added.
So we just take this 20, so we'll make it over here. So the 10 just add.
You want to see them? Yes. Okay, about 1 more minute here. Okay, everyone submit. Okay, so we have a saturated solution of iron 2 sulfide and concentrations of the ions. I wrote out the equilibrium equation here. So iron 2 sulfide formula is FeS, forms Fe2 plus in S2 minus. So the KSP is concentration of each of those ions. There are no coefficients. Everything's in a 1:1:1 ratio, so no exponents. So now we're just plugging in values. So this one is 1.6 times 10 to the negative 19. Now, if something it's more soluble and less of it remains a solid, we're talking about relative solubility here, less of it would remain a solid, more would become ions. So generally, you'd say if something has a higher KSP, it is a more soluble solid. So if these two values are higher, then the KSP will be higher. So higher concentration of ions, more soluble solid. But there are some conditions of when you can compare two compounds and when you can't. And the issue is if there are exponents in one KSP for one solid and no exponents in the other, or different exponents in general. But if the exponents are the same, then you can directly compare. So this is all summarized on this next slide. So KSP is a measure of solubility, where a lower KSP would mean the solid is less soluble. Sometimes. So there's a caveat to that. The KSP values of two compounds, so comparing the solubility of two compounds based on their KSP values, that can only be done when each produces the same number of ions in solution. So we're thinking about for every one solid ionic compound formula, how many ions does that break into? So of these three solids below, which could you compare the KSP values directly? Well, we need to think about if calcium sulfide is added to solution, it would form Ca2 plus and S2 minus. If sodium sulfide is added with that 2 subscript here, that tells us for every one solid compound, we have 2 sodiums and 1 sulfide. And then for our last one, we have 1 magnesium and 1 sulfide. So of the 3 solids below, the 2 that you could compare directly is the first one and the last one, because they both produce for every one solid 2 ions. Sodium sulfide would produce 3 ions. So that would mean that we just can't compare directly. There will be an exponent in the KSP calculation different from the other 2. One way to compare across compounds, even if they produce different numbers of ions, is with molar solubility. So this is on the next slide, and we'll go through that here. So KSP we've been talking about. This is a measure of solubility, and it is what we said, concentration of the ions present in solution raised to the power of the coefficients, the product of that. Solubility, so this goes back to an earlier chapter. Remember we're talking about unsaturated, saturated, and supersaturated solutions. So solubility would be the amount of a substance that is dissolved in a saturated solution of that substance. So it depends on the volume of the liquid that's present. So it can change based on temperature, it can change based on volume, the amount of that substance dissolved. Molar solubility is more standardized. So it's the number, we can assume at room temperature, the number of moles of a substance that dissolves in 1 liter of solution. So just like molarity for concentration, molar solubility is number of moles dissolved in 1 liter. So let's go through this question. We are calculating the molar solubility of the solid. So molar solubility describes a solid, but we need to know concentration of ions to calculate molar solubility. So we have KSP, which is very similar to when we did equilibrium concentrations in the past, or equilibrium calculations in the past for an acid where we were given Ka. And we could calculate amount of acid present at solution or at equilibrium using the Ka, using also an ice table. So last ice table for our notes this term, I think, is right now. So we are starting, we'll assume, with excess solid. Because we know that this compound, while the KSP is pretty low, right? It's less than 1, 10 to the negative 7. That means that if barium fluoride is added to solution, most of it stays as a solid. So we can just assume there's a lot of solid present, and we're going to worry about how much ions are generated. This will dissociate into barium 2 plus and fluoride minus. So now, when barium fluoride dissolves in solution, the amount of the solid present will decrease by a number, and that number that it decreases by, that's what we're looking for in this scenario. Barium ion will increase by x, and then fluoride will increase by 2x because for every 1 barium fluoride we form 2 fluoride ions. That's a balanced equation. So now we need to solve for x. We'll use KSP. So I'll do this on the right side. So we got barium 2 plus F minus squared at that equilibrium in solution. So this is x times 2x squared. And this is equal to, oh, the square should be on the outside of the parentheses. So that square applies to the 2, making it 4, and the x making it x squared. We multiply by that other x. So KSP at equilibrium is 4x cubed. So 4x cubed is equal to KSP value 1.84 times 10 to the negative 7. So x, we divide by 4, and then take the cube root. The value here, 3.58 times 10 to the negative 3rd molar. This is the amount of moles of, well, it's X, right? The amount of moles of barium that was, barium ion that was formed. these are in a 1-to-1 ratio, so it's also the number of moles of barium fluoride that's associated. So this is the molar solubility of BAF2. Okay, we will finish up 17 and start 18 on Wednesday, so keep a look out for those slides. They'll be available by tomorrow. And then we'll do or talk about those review questions on Wednesday as well.